Live. Okay, so again, recap quick. Differential equations is what we're playing with. And here I have the rate of change of a function is proportional to the function itself. We can separate the variables. X is on one side, Y is on the other. And you can pause this video and take a look at my solution here. That leads to exponential growth here. And with population dynamics, which I'm getting to next, that is a problem. And so this part right here, you think about what this part of the equation does. N is what we call the carrying capacity. And so it is the maximum sustainable population. Now we have to have some kind of guess at that, okay? Given some kind of guess on that, as X gets closer and closer to that, right, then this multiple right here gets smaller and smaller and smaller until what happens when X reaches the carrying capacity? I get N minus N, which is 0, which means no growth. If X happens to exceed the population, maximum population, then this becomes a negative number, which means we have a decrease in growth, okay? And so often there's a couple of ways of logistic growth. Ideally, with logistic growth, it looks like it increases exponentially at first, but then it reaches this critical point and then it starts to reach its maximum. And so there's a horizontal asymptote here at whatever the maximum population we believe is. Okay, so we get this S-shaped curve. In reality, what happens is we get more of an oscillation. So if this is the carrying capacity, the population starts increasing toward that, it goes over it, right? So all of a sudden, you haven't exceeded the resources yet, but once you have too many people, all of a sudden resources become very limited, populations get too dense, diseases increase, things like that, and then the population starts to decrease and drops down again. Then it's below the carrying capacity, the environment recovers, and then the population starts to increase again, and you get this oscillation around the carrying capacity that it gets tighter and tighter towards, okay? And there's been studies on this in a variety of scenarios in laboratories with like fruit flies and then out in nature too. So, so this is a popular equation in terms of modeling how things change over time in particular populations. Next thing, mathematically, can we isolate the x's from the t's in this equation? And the answer is, well, there's no t's on the other side of the equation, so yeah, I can. Okay. Sometimes the equation could also be time dependent. This one's not. So I'm going to rewrite this one similar to the way I did the last one. I'm going to take this chunk of x times n minus x, and I'm going to divide it to the other side. So I'll have 1 over, oops, x times n minus x. I'm going to leave the dx on that left side there, but I'm going to multiply the dt up to the other side, so I get k times dt. So this is what we call a separable differential equation, because I could get all of one variable on one side and all of the other variable on the other side. From here, I can then think about integration on both sides. And then it becomes, can I find an antiderivative for this right here? Okay, so let's see. If I rewrite that a little bit, what's it going to look like? I'm going to have a 1 over, let's put the x squared first, so I could say it's a negative x squared plus nx dx. The other side's easy, right? K times dt, no big deal. So I have two different ways to look at this one. I could either look at it this way right here, which means what method would I use to solve that one? The partial fractions. Yeah, partial fractions is perfect on that one. If the equation's in this form, what might we apply to that? Any thoughts? What's that? Trig substitution. Yeah, if I complete the square on the denominator, then it's set up for trig substitution. Okay, so I got a couple of different ways I could attack this one. Let's take a look at partial fractions, and then we'll look at the trig substitution in a slightly different way. So new page. oops, wrong color, wrong tool. So I have the integral. Actually, we don't need the integral yet. I just need to think about 1 over x times n minus x. And that, according to the theory of partial fractions, since the degree of the numerator is less than the degree of the denominator, should be equal to some number a over x plus some number b over n minus x. And then our standard routine for solving these suckers is to multiply everything by the common denominator, which is x times n minus x. Ooh, that's a weird x. N, sorry. And I have to distribute that through to each of these terms. And lots of stuff cancels. So I should have 1 on the left. On the right side, the x cancels. So I'm going to have a times n minus x. And then b over n minus x, the n minus x cancels, leaving just the bx. And then we have 2 choices from here. We could either collect like terms or we could pick convenient values for x. Does anybody have a favorite? I really like convenient values, yeah. Yeah, right. Otherwise, yeah, no matter what, you get a system of equations. So here, I think I would let x equals 0. That's pretty convenient because then this term goes away. And that's going to lead to 1 equals an. And that implies that a has to be 1 over capital N. And then next convenient x value, yeah, capital N there. And so then this term zeroes out, and then I get 1 equals bn. So check that out. B is also equal to 1 over n. So that means I can rewrite, oops, I missed my b there, bn, 1 over x times n minus x as, I'm going to write it as 1 over n times 1 over x plus 1 over n times 1 over n minus x. And so I'm just going to factor that 1 over n out. And so it's just simply 1 over x plus 1 over n minus x, which is not too bad to integrate. So integrating that thing right there, I'm going to pull the 1 over n out. So I have 1 over x plus 1 over n minus x dx. I get the 1 over n hanging out, and then natural log of the absolute value of x. And then what happens next? Plus natural log of the absolute value of n minus x. But we got to pause. The derivative of x with respect to x is 1, no problem with the chain rule. But the derivative of n minus x with respect to x is a negative 1. There is no negative sitting out here. So I'm going to have to throw a negative in there to compensate. And we're going to have a plus c. And then this is going to clean up a bit, because basically I have the difference of 2 logarithms. So next page, oops, I have 1 over n times the natural log of the absolute value of x over n minus x, and then plus c. Now here we've cleaned up the left side of that equation. We just calculated that guy right there. We next need to calculate that right there. So what's the integral of k with respect to t? Just be kt. So this is equal to k times t. Now we could do a plus some other constant here, but we'll just throw it all into 1. So just having a plus c on one side is sufficient. Okay. And then let's see, what do we want to do here? X is our dependent variable. So if we can solve for X, let's try. So let's see, if I want to solve this for X, I need to get everything away from the natural log, so I'll have to subtract that c to the other side. Oh, actually, you know what? It makes more sense then to just take that plus c and put it on the other side, doesn't it? It's just some constant. We don't know where it is. It doesn't matter whether we call it plus c or minus c. So let's look at it this way. So then to solve for X here, I got to get rid of the 1 over n. Now, by the way, that kind of algebra you can't get away with in regular algebra class. This is only a consequence of calculus that we can get away with that. Okay, so warning, any algebra students watching this in the future, that's not legal algebra unless you're doing calculus. Okay, so I'm going to multiply both sides by n. So then I get the natural log of the absolute value of x over n minus x is equal to n times the other side. So capital N times k times t plus, you know, n times c is just some other constant. I'm still going to call it c. So c is like, those constants are like black holes in calculus. They just suck everything in. That's constant nearby. It's a trash bin, yeah. It's still our constant. And then to get rid of the logarithm, I exponentiate both sides. So then I'm going to say e is the base of each side, and those are the powers. So doing that, I get absolute value of x over n minus x equals e to the power, and I'm going to separate on the plus, e to the power nkt times e to the c. And e to the c is just some constant. So we're just going to keep calling it c. Crazy stuff, huh? I remember that blew me away in Calc 2, and then there's a class called differential equations where all you do is solve equations like this, and you're regularly just, the c keeps morphing. All right, now since I have a constant multiple there, I can get rid of the absolute value because the c is going to suck up whether it's plus or minus. Okay, so then I'm okay to just say, I don't really need you anymore. And here's where the exciting times come. We have two x's here, and they don't just cancel. Okay, so the only thing I can do is multiply the n minus x to the other side. So I'm going to get x equals, I'm going to call that c times e to the nkt times n minus x. So I got the x out of the denominator. I got to get it to the other side, but I can't do it by division. That's puts me back where I started. I have no choice but to distribute here and then use addition and subtraction to move things around. So this is going to become x equals n times c. That's just a constant, right? So that's just going to be c e to the n kt minus c times x times e to the n kt. And now I can add that x term over to the other side. So I'm going to go to a new screen. So then I've got x plus c times x times e to the n kt equals c times e to the n kt. And I think maybe I shouldn't have done that. Is that going to matter? I'm a little worried now that I have two different c's here, and one is really nc and the other is just c. That might matter because there's more than one of them floating around in different spots. That's making me nervous. So we'll call it nc then. Let's not let that black hole suck that in. Yeah, that frightens me. I can't do that. All right. So that means that's this guy right here, right? So that's NC there. I think so. Nope, the other one has the NC. Oops. Thank you for paying attention. N is over here. Okay. I have the x's together so I can factor out the x. And then I'm going to get a 1 plus C e to the n kt equals n c e to the n kt. And we are almost done. We just have to break that multiplication by dividing. Oh my, where'd that extra e come from? Whoa. There we go. Yeah, e to the e. Yeah, those come up. Like today, we're going to see a log of a log. That happens too sometimes. So finally, we can say x is equal to nc e to the nkt divided by 1 plus e to the nkt. And an alternative version of this that floats around is, notice the e to the nkt is in multiple spots here. If I multiply, question, did I make a mistake? Oh, there's supposed to be a C here, isn't there? C, yep, and then there's a C here, thank you. Yep, that C needs to be there. Often you'll see this written slightly different. If you multiply top and bottom by e to the negative ktx, then what you end up with an equation that looks slightly different. It would be the NC stays in the top, and then I would get an e to the negative nkt, e to the k nkt times e to the negative nkt is 1. So then down here I would just have a plus c. So that's another form of this equation. Often people also divide that c out and then it'll appear over here. So there's lots of different versions of this equation algebraically. This is a more common version right there. So just for fun, I'm going to graph a simple version of that in GeoGebra. So fun with algebra, more algebra in the next section. So let's see, let's pick some simple numbers. So we'll let it be, how about just 1 over, let's do just e raised to the negative 0.1 t maybe, and then plus 1. Oh, what? Oh, t, it doesn't like t, right? I need an x in this system, x. Okay, and then this is GeoGebra, so I can rescale quickly. So I just want to show this has the shape that I was mentioning. So see that S kind of shape there, where it's reaching up to its limiting population. So here I set the limiting population to be 1. Could be 1 billion, 1,000, whatever. And here I have the exponential stuff, you know, that slow increase starting over there, but imagine this whole thing sliding over. So this is, again, it's exponential growth at first, but then we've hit that limiting ceiling because environments can only handle so much of a particular population. All right, that was exciting algebra. Whew. All right, let's take a look at some other stuff. How about, let's see, and I need some other tools, resources page. So there's 2 sets of tables that are going to be helpful in the next set of homework for section 8.5. We were using the derivative formula sheet here. I added an online integral formula sheet, and there's tons of them online if you look around. And the book comes with one too. Let's see, did I already open it? Oh yeah, over here. So I think it's in the back of the book. Brief table of integrals. And let's expand you. Where's the expand button? Oh, interesting, you disappeared. Huh. View, zoom, width, that's better. So last week you guys started building your own integral table based on the one that was started in the beginning of chapter 8. Here is a more extensive table. So our book has how many integrals? Quite a few. 157 of them. Okay. When I was in college, the integral tables were a little bigger because the computer algebra systems didn't really exist yet, and so there were actually books of integrals that engineers would, when they had to solve a problem, would just look through the book until they found something that was close enough to their problem, and they would do algebra to make their problem look like the one in the book. That's the way we did them. And it was all based on somebody else's hard work to come up with the formula in the first place. Okay, yeah. So so there's the book one. Let's see what my online one has. Basic integrals, trigonometric integrals, exponential and logarithmic, hyperbolic, inverse trig, integrals of a squared plus x squared, integrals of x squared minus a squared, integrals of a squared minus x squared. Let's see, linear integrals. Oh, this one's a little shorter. This one only has 113. So, you know, you go to websites, you'll find websites that probably list thousands of different integrals that you could use to solve problems. So mostly what we're going to do is we're going to say, okay, which integral in the table does the one we have look like? And then can we do a little algebra if it's not exactly? So the first one we're going to take a look at and see what we can find in the table. So if you have your book with you, whip it out. If you don't have it with you, then you're stuck with me scrolling through the table. So the first one we'll take a look at. And then somebody might ask, well, why should we look in a table when we have Wolfram Alpha? That's a good question, and I don't have a good answer to that one. Mostly we're going to use Wolfram Alpha, but we're going to do a couple of these book ones. We have Google. Why do we need a table? And somebody had to program this stuff somewhere along the line. So basically, we're going to be integral programmers here. 4x minus x squared dx. It's somewhere near the end of the book. Yeah, it's one of the last appendices in the book. So let's see, my online version of the book shows it on page, it's T1, yes, T1 through T6. All right, so let's see. Here we have x times the square root of a quadratic is the one I'm looking at right here. So x times the square root of a quadratic. Is there something like that in our table? So write that integral down, and then we'll use the integral table, and then we'll ask Wolfram Alpha what it thinks. And what else do we? Mathway does quite a few integrals, right? But I think it gets stuck way more than Wolfram Alpha, is my recollection. Because I tried giving it some that I thought it would stick it. Wolfram Alpha could do it, Mathway could not. All right, so let's see. Looking at the table, and so sometimes things are organized into, here we go. So I'm in the 50s here, and I'm seeing something that looks promising. This one is an x squared minus an a squared. Oh, I have an a squared minus an x squared, essentially. Unless they have, sort of, let's see, where would that be? Was that the next section or the first section? A squared plus x squared, a squared minus x. Oh, here we go, in the 60s. Whoa, I don't like the way this scrolls. Not there. Am I in the wrong section? X squared minus a squared. The problem with that, where are you? That's down in the 100s. Oh yeah, here we go. Is that ours right here? Good eyes, Darren. Yep, that's what we want. Yeah, and sometimes sometimes they're hard to spot exactly, and you find something close and morph it. Like I could complete the square on my integral and get something of the form a squared minus u squared, and I could solve it that way. So there's often more than one way to do it. All right, so we have a formula here, formula 124 in our book. Is that right? Okay. All right, so let's take a screenshot of that and see if we can apply it. So screenshot of this guy, right? 124. All right, so this is where we're going to attempt to apply. I'm curious about that other integral table I brought up to see if it has it too. Those are the linear ones. Oh, nope, there it is, right here. They write it in a different form. Notice they write it in unfactored form in terms of a quadratic. Let's just grab that one for fun too. Oh, check. Yeah, notice they have the opposite in here. This is x minus a, this is a minus x essentially. Yeah. Yeah, and that's the other thing. Anytime trig functions, inverse trig functions, logarithm, or hyperbolic trig functions are involved, there's generally going to be multiple ways to state the answer that look different. And that's just the way it is. Then it's a matter of trying to justify they're equal or just saying, hey, I like mine better than yours. That's fine. Okay. So I'm going to go with the one from our book, but we got the idea. So then we just try to equate constants in u versus x. So for this particular problem, we have our x matches our 2a here is equal to 4. So for us, a is equal to 2. And then otherwise, we just have a great matchup there. It's just a matter of plugging in and we have an answer. So we believe the answer, the antiderivative, should be x plus 2 times 2x. That would be a minus 6, wouldn't it? Yeah, minus 6 times the square root of our original square root, so 4x minus x squared, all over 6, plus we will get an a cubed, so that's 8 over 2, which is 4, and ours has a sign inverse of x minus 2 over 2, and then plus c. And algebraically, really the only thing we could do is like the other integral table did, they multiplied out that pair of linear factors into a quadratic factor. I don't see the point in that. I like what we have just fine. So next we're going to ask Wolfram Alpha what it thinks. And it's possible Wolfram Alpha could give us an answer different than both of these. Because again, there's always multiple ways to solve a complex problem. So Wolfram Alpha. Oh, by the way, the password for the homework, should you not get it done by tomorrow night, so this is what, 85 password. Oh, and I had a problem with the 83 password somebody found. Apparently you can only have a password that's so long in this system and it doesn't give you an error message. So I had originally set the password to trig substitution rocks, but that was one letter too long. And so it only accepted up to rock. So I apologize to any grief I caused anybody. Password here is Wolfram Alpha. If you don't happen to get it done by tomorrow night, you'll need that password. All right, let's ask Wolfram Alpha. Wolfram Alpha, and so we want the integral parentheses of x times the SQRT of 4x minus x squared And since it's an indefinite integral, I just close the integral parenthesis and hit enter and pray. All right. Ooh, check this out. It's different. Oh, man. And it's still thinking. It's sometimes it'll give you alternate forms too. All right, let's blow that sucker up. Yeah, check that out. So they have extra square roots. So by the way, so just let's screenshot this and see what we can do with it. Where's my screenshot button? Oh gosh, wrong thing. Where'd you go? Screenshot. We are. Let's compare this to what we have. So if you find yourself bored, we don't need the plus a constant. We know it's there. All right, let's put you right there. Okay, so just some notes on this sucker. If you multiply this inside out there, you basically get the same as our starting the inner part of the quadratic. And here they separated it, which is a little bit dangerous because that's only true if both pieces are positive. So they get some weird algebra going on in there. Same thing down here. Ooh, interesting. Here they are as the log sum inside, which doesn't reduce. They've got this extra stuff in the bottom. Yeah, so somehow, if we equate the non-constant parts of these and set them equal, after lots and lots of algebra, we would find that, or sorry, if we subtracted them from each other, after lots of algebra, we would find that difference is just some constant. Maybe it's 2, maybe it's pi, maybe it's 6. Who knows what it's going to be? But the difference between this black antiderivative and this blue one is a constant because that's what the fundamental theorem of calculus says, pretty much. Actually, it's more what actually not the fundamental theorem that tells us that. It's is it the mean value theorem? I think it's the mean value theorem that leads to that conclusion. Let's see. Did it give a? Oh, that's another one. Okay, here's another form there. Ooh. And here's other forms here. Yeah, so Wolfram Alpha likes using log. And here, do you know what remember what log means? It's the natural log, right? We got to keep that in mind. It's the natural log. Yeah. Oh, here's another version. And a complex version. Oh, we don't want a big O as a whole nother story. We don't want to go there. Yeah. They're bringing in new big O is an interesting function. Okay. Integral calculator. Integral calculator. I have not seen this one. Integralcalculator.com. All right. All right. So let's see. And it just wants the integrand. So we're going to give it x times the sqrt of 4x minus x squared. And then, oh, look, it makes a pretty version on the fly. Oh, this is cute, except for that video there. Go. And then please wait, calculating result. And okay, yeah, this gives us our version, arcsine. Okay. There's another arcsine, another arcsine. Yeah, and it turns out if you throw complex numbers into the mix, then there's a relationship between trig functions and e in the natural log. And if anyone takes next calculus 3, I'll show that relationship there. Will they really show steps? Oh my gosh. Nice. There's a reason I love this website. This is a great website. It tells you what you're doing, it tells you which part. Wow, this is awesome. And then they do hyperbolic substitution. Oh my gosh. Use the power reduction formula. Man, this is pretty cool. Okay, so that's pretty cool. All right, so everybody, I need to add this to our list of resources. This is wicked cool. Thank you, Darren. Okay, edit. So that's totally legal on a take-home test, but not an in-class test. All right, where do we put that? Probably under Wolfram Alpha. Integral calculator. All right, it is linked on other stuff in the resources section. All right, so we are out of time for fun with math today. So tomorrow we're going to play more with Wolfram Alpha and those crazy tables. Have fun with the homework, and I will see you all soon. That's a fun website.